Hello, everyone. Thank you for being here with us today to join me in this presentation. Today I'm presenting my paper titled Implementation-Oriented Feature Selection in UNSW NB15 Intrusion Detection Dataset. My name is Mohammed Alani. I'm a professor of cybersecurity at Seneca College in Toronto, Canada. First, we'll start with the abstract of the paper. We know that statistics show us that about 30,000 websites are breached every single day on average in 2021, and security challenges have grown a lot in difficulty and complexity. And UNSW NB15 is a data set that was used a lot in creating machine learning based intrusion detection system. So what we will do in this research is that we will try to produce a reduced version of UNSW NB15, and that reduced version would help us achieve high accuracy while maintaining a low training time and low inference time. So at the beginning, we'll take a quick look at UNSW NB15 dataset and get some background information about it. It was introduced by University of South Wales, Australia in 2015. It includes raw network flows, about 2.5 million raw network flows that include a lot of different types of attacks. The number of features that were extracted in the original dataset is 49. And taking a quick look at this table shows the different fuzzers, reconnaissance attacks, shellcode analysis, backdoors, denial of service, exploits, generic and reconnaissance, and worms. Now, when we examined the data set, we found that the high imbalance between the specific types of attacks can cause problems in machine learning. As you know, when we have an imbalanced data set, the accuracy gets a big hit. So in our work, we decided to split the whole data set into two categories only, which are benign and malicious, so that we gathered all of the different types of attacks under a single category so that we can generate more of a binary classifier. So in the paper, you can find a lot of different previous works that we have discussed, but I'd like to mention in particular these three that are considered significant. The first is coming from the same author that presented the data set itself, presented a paper discussing the features that they consider more significant. The study focused on replicating these features of NB15 data set into KDD99 so that it would be used as a benchmark to measure how well these features are selected. In 2020, Kasongo and Sun published a paper that proposes a filter-based feature reduction techniques using XGBoost algorithm. And in 2020 as well, Al-Moumani published a research paper proposing feature selection model based on particle swarm intelligence, including Grey Wolf optimizer, Firefly optimizer, and genetic algorithms. Moving on from the previous works, we take a look at the pre-processing stage. To me personally, I think that pre-processing stage is the most important stage in deciding the success of a machine learning model because it prepares the data for success. So here is what we did based on the observations that we made about the data set. We started with the original data set with 2.5 million instances, 49 features, and the intended output is a balanced data set. So we started first by looking at empty features and removing them. And that was the first stage. Whenever we have empty features or missing data, basically, we removed these instances, and then we moved on to do undersampling so that we can achieve balance. You can clearly see out of the 2.5 million records, there were about 2.2 million records for benign data and about 300,000 malicious data only. And this imbalance will cause a lot of problems in creating the classifier model. So we moved to random undersampling to reduce the majority class, which is the benign labels. And then we converted some of the non-numerical values, such as source IP address, destination IP address, to decimal numbers. And then we did label encoding for some of the features that were text features, such as protocol type, state, and service. And the last stage was to check, because we noticed that some of the port numbers that are mentioned within the data set were actually written in hexadecimal representation. So we converted them into decimal representation. That concludes the data sets pre-processing. So after pre-processing, we were left with 89,000 instances, 67,000 of them at the benign label and 22,000 with the malicious label, and the number of features was 48. Now we talk about our proposed feature selection. The proposed feature selection was basically successive feature reduction using feature importance. So what we did is that we trained a random forest classifier. Then we extract the feature importance from that classifier after training. What we do then is that we select the feature with the lowest feature importance, and then we would eliminate this feature, and we go back to retraining and re-evaluation of the feature importance, and then removing the least important feature. And this process is done repetitively so that we can reduce the number of features. But the idea is that we didn't want to reduce these features directly by, for example, training the random forest, then selecting the top 5 feature importance and using them for the final data set. But instead, we did it successively, so that if there is any type of correlation between these features, we don't want them to be eliminated directly. We want to eliminate them gradually, so that we make sure that this correlation between these features is taken into account. So we do the target features. We set the target features to 5, and in a moment you will see why we selected specifically 5. We delete the features, and then we go back and we do a random split of training and testing data. We retrain the model again, and then we choose the feature with the least importance, and we eliminate that. So as a result of this, you can see this is the F1 score, the F1 score, average F1 score change with feature reduction. You can see, even though I know that the graph shows like there is a huge decline, but actually it's a very minimal decline, because we started at 0.997 and we ended at 0.995, 9959, actually 9959. So the idea is that the accuracy of the system was highly maintained, so that we ended up with 99.6, almost 99.6 F1 average F1 score. And please take into consideration that this average F1 score is actually weighted average. You can see here the accuracy that is produced even by all the 4 different types of classifiers was very high. random forest and logistic regression and the other two classifiers as well. We can see the F1 score was very high. False positive is very low. False negative is also very low, which is extremely important in intrusion detection data sets. You can see that the 5-feature model did not impact accuracy that much. You can see 99.78 when here it's 99.69. The logistic regression one did take a hit in terms of performance, but our top performer was random forest. Even after the reduction, you can see the false positive and false negative remained way under 1%, which is great. So the produced data set was 89,533 instances with 5 features only. This, of course, caused great improvement in terms of training time, in terms of testing time. And we can see here this comparison of our proposed model in comparison with the other models that were provided in previous works. We can see that the timing, in terms of timing parameters, our proposed model was very much superior. In terms of performance, it was much higher than other systems. Finally, we take a look at the conclusions. We proposed implementation-oriented reduction of features, produced a data set of 89,000 instances with 5 features only, and testing demonstrated that high accuracy achieved did not deteriorate after the elimination of 43 features. It also showed that there was a noticeable reduction in training time that exceeded 60% in most algorithms, while testing time witnessed a reduction ranging between 8 and 77% in most algorithms. I believe that's all I have for now. I encourage you to read the full paper and feel free to email me any questions that you have. Thank you very much for being with us today.